and that was basically that we had started to look at universal natural laws that apply to all matter, to all continuum matter. So last week I think I'd introduced to you guys that we will be looking at, there are basically 5 universal principles, and we are going to be looking at these 5 ones. इसके अलावा भी छोटे छोटे इधर उधर और भी हैं. So for example, I know there is also a just before the first law of thermodynamics, there is actually a 0th law of thermodynamics as well. But I think that 0th law can also actually be proved from the second law. So something along those lines, which is why we're not going to be considering it. Okay, so these are the 5 that we'll be looking at, and what we had started to do was, because of course I'm pretty sure that all of us have seen these in one form or the other before in our life, before Continuum Mechanics ME803. So the purpose of looking at these things again here is that most of the time when we had looked at these in our undergraduate education, we were looking at them for finite bodies, for particles. We hadn't really been formulating them for infinitesimal elements. So that's what we've basically started to do here. That we've started to formulate these for that, that concept that we'd introduced, that we are dividing up our continuum into an infinitesimally until we get to like a infinitesimal element. So that's what we're doing. We're defining these principles or conservation laws for our infinitesimal either material element or our infinitesimal control volume, basically. So yes, so last week इसी तरह हमने we defined our conservation of mass, और इसीलिए I think अगर आप लोगों को लगे कि ये तो थोड़ा अजीब सा लग रहा है, इस तरह का तो नहीं हमने conservation of mass देखा हुआ, so वो उसकी precisely यही वजह है, because this is conservation of mass for an infinitesimal control volume. Okay. So that's why it has this interesting form where we've got the rate of change of the density and the velocities, the divergence of the velocity coming in. So, right, so we did talk about this last time. So today I'm going to move on from our next principle. I just want to remind you guys that the conservation of mass key, the equation that we get in for the infinitesimal control volume is known as the continuity equation. And we also discussed in detail how we can express it in 2 formats, one being with the material derivative, the one in the red box right here, and the other being with the rate of change of the density in the control volume. Right, they both represent the same thing. Okay, so guys, keep an eye on your mics unless you have a question. Okay, so the second principle that we're going to look at right now is the principle of moment of momentum, or the principle of angular momentum. Some of you may recall that this quantity right here, the moment of momentum, is actually the angular momentum of any particle or body. So we are looking here at the balance of the angular momentum. Yeah, but to put it simply, rather than saying it in such a weird, fairly complicated way, we're essentially just looking at the moment equilibrium for an infinitesimal material element, essentially. Okay, so let me draw out my material element, or first of all, what I'm going to do is, as you guys can imagine, when we're looking at moment equilibrium, moment is a vector, right? So if I have like a net moment acting on a particular infinitesimal element, it is going to have each of its components in the 1 direction, the 2 direction, and the 3 direction, such that when I say moment equilibrium, I actually mean that I have M1 is 0, M2 is 0, and M3 is 0. So what I'm going to do first of all is just look at M1. Okay, so that is going to be the moments about the x1 axis, or what that means is when I'm looking at this element, iske na x1 axis bahir aa raha hai, like so. If I use my right hand grip rule, then my x1 axis is coming out, and then I have x1 is coming out, x2 is going to be like this, and this is going to be x3. So this is my coordinate system defined like so, and I'm just looking at turning effects about the x1 direction, moments about this direction. Now for this infinitesimal element, let me draw out के हमारे क्या क्या stress components उसके faces पे act कर रहे हैं. Now of course this is my 2 face, ये वाला. So I know then that there is the sigma 2,2, sigma 2,3 acting on it, but there's actually also sigma 2,1 acting on it. लेकिन ये sigma 2,1 है ना, वो कोई turning effect नहीं produce कर रहा about x1. इसलिए I have ignored it and I haven't really drawn that in. And instead all that I've drawn is I've popped in all of my stress components which are causing turning effects, which are causing moments about this x1 axis coming out of the page. Thick, right? So with that, now let's look at it. So of course, a moment, आप लोगों को सबको पता है, moment is force times the moment arm from the axis of rotation. So it is, remember, it's force times the moment arm. So when I'm just talking about the turning effect of oh yes, मैंने sigma 2,2 भी draw किया हुआ है. When I'm talking about the turning effect of the stresses, I do need to convert them from stress to the force on which they are acting. So looking at that clearly, sigma 2,3 जो है, that is acting on this area. So इसकी वजह से जो force है, let's say dF23, that is going to be sigma 2,3 multiplied by the area of this face, which is of course just what, into the page क्या होगा, delta x1, और इसकी ये direction क्या थी, ये x3 direction थी. So this would be delta x3. So that is sigma 2,3 multiplied by, either I write down dx1 dx3. This is the total force because of sigma 2,3. And then the moment arm that this has from my axis is what? It's this length. जो कि क्या है, ये पूरा फेस जो है dx2 है, क्योंकि ये x2 की डायरेक्शन में, ये देखें ये रहा x2. So the moment arm of this is then dm23 becomes df23 multiplied by delta x2 divided by 2, या फिर dx2 by 2. But also noting के ये तो मैंने अभी sigma 2,3 के लिए moment derive कर ली, but similarly we're gonna have other moments acting because of the other stress components. So just if you understand the process, we first convert the stress into the force, then multiply it by its moment arm. We can do the same thing for all the others. Now I just want to note, I made a mistake. मैंने आपको पहले कहा था मैंने वो बाकी stress components नहीं बनाए, लेकिन मैंने गलती से बनाए हुए हैं. So just noting कि ये जो normal stresses हैं, such as sigma 2,2, they pass through the point about which I'm taking the moments. So sigma 2,2 का तो कोई moment arm नहीं होगा. उसी तरह sigma 3,3 is also going to pass through it. इसका भी कोई moment arm नहीं है, और ये तो हैं ही, इनके कोई moment arms नहीं है. So the only components I have are sigma 2,3 acting on the right face, sigma 2,3 acting on the left face, sigma 3,2 acting on the top face, and sigma 3,2 acting on the bottom face. Right? So just summing up the total moments caused by each of these, I get this expression right here. Okay, that is जो sigma 2,3 का मैंने पहले निकाला था dm23, वो उतना ही जितना इसने turning effect cause किया to the in the anti-clockwise direction, the same amount is being caused on the left face. That's why वही sigma 2,3 वाला multiplied by 2 हो गया. या फिर you could just treat these two like a couple. Or couple का I think some of you may recall कि the moment caused by a couple is actually the magnitude of the force that is in the couple multiplied by the perpendicular distance between the two forces. So इसमें total distance is just this del x2, hence why this 2 and 2 would cancel out. And similarly, the same thing applies with the two times the moments being generated by sigma 3-2. So ये sigma 3-2 जो है, it is causing a moment in the clockwise direction, as you notice. It's causing moments in the clockwise direction. So I get a minus right here. Or simplifying this, I think we can see that all of them have the dx1, dx2 या फिर मैंने delta लिख दिया, same thing, just the infinitesimal material element की lengths. So these all cancel out, and eventually basically if you spot it, the only thing that we're left with is that the stress sigma 2-3, this one, is actually equal to the shear stress on its adjacent face. That is sigma 2-3 is actually equal to sigma 3-2. And if I do the same thing and I find the moments or the net moments about the x2 axis and then about the x3 axis, I get a similar and corresponding result for each of the other shear stresses. And that is that I see that sigma 1-2 is actually equals to sigma 2-1 and sigma 1-3 is actually equal to sigma 3-1. That is, if I write down my stress tensor as we know from beforehand, then we just discussed sigma 2-1 is equal to sigma 1-2. इसलिए इसकी जगह मैंने सीधा sigma 1-2 ही लिख दिया है. फिर sigma 3-1 जो यहाँ पे sigma 3-1 की term होनी थी वो is equal to sigma 1-3, इसलिए I've just written down sigma 1-3 here. And similarly this last one, so ये sigma 3-2 is actually equal to sigma 2-3, so I can just pop that here. That is to say, in other words, that this Cauchy stress tensor is actually symmetric. और हमें सिर्फ और सिर्फ, that is, sigma is equal to sigma transpose. It is symmetric. And it only thus has 6 independent components, ये वाले 6, acting on an infinitesimal element. Now I know you guys, some of you already know this. Also, we had briefly mentioned this beforehand as well कि Cauchy stress tensor actually symmetric होता है, इसलिए पहले हम थोड़े से उसके order को manipulate कर रहे होते थे उस तरीके से. But now we've just got our proof कि why is it exactly symmetric? It is because of imposing moment equilibrium for an infinitesimal material element. ठीक है जी. Now I just want to make a little comment here, which is that some of you may recall that we had already seen that the infinitesimal strain tensor जो था, this one, this was also symmetric. Epsilon was also symmetric. लेकिन epsilon का symmetric होने का reason था उसकी definition. Why? Because this was the displacement gradient का जब हमने symmetric और anti-symmetric part में उसको decompose किया था, recall? So उसके अंदर जो symmetric part था वो we had taken to be our infinitesimal strain tensor. My point being कि for the infinitesimal strain tensor there was no principle which was dictating that it should be symmetric. It was just by definition. We had defined it to be the symmetric part of our displacement gradient. And that's why it was symmetric. Whereas for the stress tensor, it's not by definition that the stress tensor is something which is symmetric, but instead the stress tensor is symmetric because of the laws of physics or the laws of nature. Okay, it is symmetric because of imposing moment equilibrium for an infinitesimal element. Okay. Does that make sense, guys? No response. Okay. Just हाँ जी कोई कोई बोल ही नहीं रहा था तो I thought if I'm talking to myself I might as well just keep carrying on talking to myself. Adnan, sorry.
मैम कह रहा हूँ रिपीट करते हैं
ओह है अच्छा मैं समझी थी आप कहेंगे हाँ बिल्कुल क्लियर है 10 दफ़ा एक ही बात कहना बंद करें. I was just saying that the infinitesimal strain tensor that was also symmetric. हमें पहले से ये बात पता है हमने उस वक़्त देखा था लेकिन उसकी सिमेट्री का रीज़न ये था कि the infinitesimal strain tensor was the symmetric part of the displacement gradient. That is by definition it was something which was a symmetric tensor. Okay? जब हम कह रहे हैं कि वो सिमेट्रिक पार्ट है इस प्रॉपर्टी का तो फिर तो ज़ाहिर है उसे सिमेट्रिक ही होना है ना. वेयरएज यही जो उसका सॉर्ट ऑफ स्ट्रेस कॉन्जुगेट है मतलब ये कि स्ट्रेस टेंसर जो है ये तो आई थिंक यू गाइज ऑल नो कि स्ट्रेन और स्ट्रेस का आपस में कोई इवेंचुअली ताल्लुक निकलना है लेकिन the stress tensor that is also turning out to be symmetric but not by definition. We did nothing, we didn't impose any sort of constraint on what the definition of the stress tensor should be, but instead it also turns out to be symmetric just by because of the laws of physics. It turns out to be symmetric because we are imposing moment equilibrium for an infinitesimal element. Okay. ठीक. Now that leads me to a next part which is के क्या हुआ महताब? Mahtab, can you hear me? At least Anand could hear me. So, Mahtab, we can't hear you in case you're wondering. Okay, right. So let me just jump to the other part, which is कि ये moment equilibrium हम impose ही क्यों कर रहे हैं? Now, that's actually a slightly more complicated aspect, and I'd really ask you guys that if you're interested, why are we constraining moment equilibrium for an infinitesimal element, to look this up a little bit in more detail. So to look up the principle of angular momentum being applied for our infinitesimal element. In particular, just for people who might be interested in this, I'm gonna recommend कि आप ready का ये वाला पढ़िएगा, ठीक है? उससे आप लोगों को थोड़ा सी understanding मिलेगी कि moment equilibrium infinitesimal elements पे क्यों why is it such a good assumption at this scale? Okay, just a little hint for some people. Okay, moments actually depend on the moment of inertia of a volume, right? So the thing is that the volume is so small कि जब हम इसके moment inertia second moment of area लें या moment of inertia निकालें, that turns out to be extremely, वो ज़ाहिर है उसके अंदर moment of inertia के अंदर to the power of cubes and fours आ रहे होते हैं infinitesimal lengths. So that's why the moment for an infinitesimal element goes to 0 essentially. Okay? Again, I'm just saying for those who are interested why there is moment equilibrium at an infinitesimal scale, you guys should look it up. It's interesting, right? For the others who are not interested, then just take my word for it that at the infinitesimal length scale, there is going to be moment equilibrium. Even if globally वो कोई चीज़ rotate कर रही है और globally there is no moment equilibrium. Okay.
मैम बात मुझे आपसे पूछनी कि आप कह रही हैं कि पावर जो है -4 और -3 में जा रही है, तो इसका एसेंशियली इतना M1 जो है ये 0 आ रहा है, तो वैसे भी अगर इक्विलिब्रियम को पॉट किया तो 0 नहीं आना चाहिए.
हाँ तो अदनान यही तो बात है कि हम लोग जनरल चीज़ों की बात करें, हमने कोई इम्पोज नहीं किया हुआ कि ये चीज़ को इक्विलिब्रियम पे होना चाहिए या नहीं. this thing can be rotating with some acceleration, मतलब इसको this could be something कि कोई बंदा है, figure skater है let's say, जो कि rotate कर रहे हो about the axis, ठीक, that is कि globally उनके ऊपर they may be accelerating, we are not imposing global equilibrium, but only when we come to the infinitesimal volume, उसके ऊपर, because of the fact that the moments do depend on the second moment of areas, for infinitesimal volumes or areas they go to zero, and that's why this assumption is approximately correct. Okay.
इसमें मुझे एक बात पूछनी कि अगर हमारे पास एरिया या वॉल्यूम इतना छोटा है तो उसके लिए क्या छोटी वैल्यू भी मैटर नहीं करेगी एज कम्पेयर टू द वॉल्यूम?
As I said, try going through Reddy's section 5.3.1. Okay, this will clarify to you. Why? Because the key for these small things is के relatively क्या हो रहा है. अगर इधर cubed है, ठीक है, ये देखें small volumes का cubed है ना, dx3 dx2, तो cube तक जा रही है infinitesimal length. So right hand side will be 0 relative to this अगर उधर वो cube से भी larger power हो. Does that make sense? So on the right hand side, if we have dx to the power of 4 or to the 5 or so on, then that is much smaller than this power, and that's why that can be considered to be 0 and so on. So the point is कि ये मैं आपको यूँ सिर्फ बता दूँ कि हाँ जी वो infinitesimal volume है, इसकी वजह से उसकी moment of inertia 0 जा रहा है, लेकिन the only way it will completely make sense to you is if you see it written out mathematically, so that you can compare the order of the differential length power कि वो किस order तक जा रही है, power 4 तक जा रहा है, power 5 तक जा रहा है, and then we will be able to judge much better. So that's why take a look at it. For everybody else, as I said, that's just something interesting on this side. For us in this course, it's just sufficient to note that on the infinitesimal length scale, there is moment equilibrium. Bas. Okay? That's it. और फिर अगर वो moment equilibrium है तो फिर we can impose it, or from that we can find out that the stress tensor turns out to be symmetric. Perfect. Okay, so I think this makes sense now that we just considered the principle of angular momentum being applied to a body, we should, or to an infinitesimal element, we should move on to looking at the principle of linear momentum being applied to an infinitesimal element. Now, please note that this principle of linear momentum is actually just another way of stating Newton's second law of motion. That is, F is equals to ma. This straightforward न्यूटन सेकेंड लॉ जो उससे हम सब बहुत familiar हैं, उसी को principle of linear momentum की terms में, that is just the rate of change of momentum is equal to the force. ठीक, और ज़ाहिर है if we expand this out we can see that there is not going to be any change in the mass, so this just turns back into the familiar version of Newton's second law. Okay, so let's apply Newton's second law to our infinitesimal element, noting that in this case for linear sort of linear momentum, that is for these accelerations a1 a2 a3, the forces का equilibrium होना ज़रूरी नहीं है body के ऊपर, ठीक है, that is the body does not necessarily need to be under equilibrium such that it may actually be accelerating. मतलब ये हुआ कि अगर हमारा infinitesimal कोई element accelerate कर रहा है, then I should tell you of course कि अगर if there is an acceleration, then there is going to be a net force acting on the infinitesimal element. Of course, F is equals to ma. So that means that the stresses acting on the infinitesimal element are actually going to be changing. So इसीलिए I want you guys to be very careful, and now क्योंकि सारे के सारे drawn in है, but just consider for now एक एक करके as I start to point out some things. So first of all, let's look at our coordinate system. x1, x2 and x3. Now let's just consider my x face, x1 face, sorry ये वाला face, और इस पे ज़रा ये red के जो corresponding हमारे 3 stresses हैं ना उनको देखते हैं. इस रेड फेस पे टू द राइट x1 फेस और ये वाले रेड जो कि टू द लेफ्ट x1 फेस के ऊपर एक्ट कर रहे हैं. Now, because there is an acceleration, there is a net force acting on the infinitesimal element, these stresses are actually going to be changing over the element. मतलब ये है कि जैसे ये normal stress की direction है, that is it is sigma 1 की direction है, but on the left x1 space. तो right वाले के ऊपर उसको क्या हो रहा है, that sigma 1 is changing, it is becoming sigma 1 but plus the small change in sigma 1 going over जो भी ये लेंथ थी x1 की लेंथ है इस डायरेक्शन में multiplied by dx1. So the original one जो इधर था to start off with plus the small change in it. और इसी तरह सब के साथ होगा for all of our stress components, that as it goes over each of these lengths, that is this is my dx1, as it goes over this one, this is my dx3, and as it goes over this length dx2, then there are going to be changes being caused in each of the stresses such that they lead to a resultant force acting on the element. ठीक है. So now let's look at what those each मतलब एक एक डायरेक्शन में क्या फोर्सेस एक्ट कर रही हैं इस एलिमेंट के ऊपर. at the same time, sorry, I forgot to mention that. So these are of course stresses जो हैं वो हमारे कट फेसेस पे एक्ट कर रहे हैं. Let me also introduce some sort of a, so मतलब ये कि वो surfaces के they're going to cause surface forces. But it's also highly possible that there may be some body forces acting on the element, such as because of gravity, because of some electromagnetic field and so on. That is, there can actually also be body forces acting, let's say, per unit mass on the infinitesimal element, such that your total body force hogi, phir that's of course just the per unit mass force multiplied by the total mass of the element, which is the density times the volume, rho dV. ठीक. So अब let's jot down each of the forces in the x1, x2 and the x3 directions. ठीक है जी कि नेट फोर्स क्या आ रही है x1 डायरेक्शन में, x2 डायरेक्शन में एंड इन दी x3 डायरेक्शन. सो पहले सबसे पहले जस्ट x1 डायरेक्शन को कंसिडर करते हैं. Now if you see, इसी से ज़रा let's start to point out what are all the forces. So this is the direction that we're interested in, the x1 direction. अब क्या क्या है? Clearly एक तो ये force act कर रही है और clearly इसी की to the left जो है वो भी act कर रही है. फिर और क्या है? ये दोनों shear stresses तो one direction में नहीं है. फिर what's here? There is this force. This is acting in the x1 direction. ये वाला आ गया. और इसी के ऑपोजिट फेस कॉरिस्पॉन्डिंग फेस के ऊपर ये वाला है फोर्स, इसकी स्ट्रेस की वजह से जो फोर्स होगी. एंड देन लास्टली ऑफ कोर्स आई आल्सो हैव ये जो सिग्मा 3 जो थर्ड फेस है, जो कि ये फेस है ना हमारे सामने, बिल्कुल सामने की तरफ इसको हम व्यू कर रहे हैं, उसके ऊपर जो स्ट्रेसेस हैं. देन टू द राइट आई हैव दिस वन और इसके कॉरिस्पॉन्डिंग बैक पे जो फेस है उसके ऊपर ये रहा सिग्मा 3 So these 1 2 3 4 5 6 stresses and the corresponding forces that they cause are acting in the x1 direction. So let's jot them all down. So as we said, the first one was sigma 1 की वाली और उसी की corresponding phase पे जो minus x direction में थी. So we popped that down. Note also कि अभी I had just briefly mentioned कि वो stress है, but we want to find the forces, right? F is equals to ma या फिर the momentum version of it के अंदर it's the force, right? Not the stress. So we need to find कि इन stresses की वजह से क्या forces act कर रही हैं, which means कि we need to find the area of those faces. So this stress is actually acting on this area, and you're welcome to try it out in this diagram to check कि वाकई हाँ ये वाला जो है dx3 multiplied by dx2 पे act कर रहा है या नहीं. Perfect. So now I think everything is clear. So writing all of those stresses and the areas on which they act down. Sigma 1 का था, फिर sigma 2 फिर उसी तरह sigma 3 वाला और ये वाला sigma 3 का दूसरी डायरेक्शन में. And lastly, of course, ये stresses की वजह से थे, that is surface forces थी. Then there's also the body force acting on it. So there's a body force का one component, B1, acting in the x1 direction. ठीक. So just adding all of them up so that we can find the net force acting on the infinitesimal element. I hope we can all spot कि if this was acting in the plus direction, this is acting in the minus direction, तो ये वाली force cancel हो जाती है. Only वो जो change in force है वो रह जाता है acting on it. So that is, I just have that change in the force, ये वाला, multiplied by the change in the stress multiplied by the area on which it is acting, which is left from all of these. ये सारे गायब हो गए. So I just have these terms left. And lastly, I have my body force. So just popping that in there. Now this is my net force, and that must be equal to my mass times my acceleration. So mass is of course the density multiplied by the volume, or acceleration का कौन सा component, because I'm looking at the one direction, it's just A1. Perfect. So I hope कि that's clear to you all, right? कि ये क्या हुआ है अभी? We just found the net force and we popped it into Newton's second law of motion. Now, acceleration and forces are vectors, so they will also have components in the F2 and F3 directions. Sorry, this can be simplified further, I forgot. Yep, all of this is, the volume is common, they cancel out. So taking this common, we get a simpler version of the previous Newton's second law of motion key equation. Okay. इसी तरह we can write it down also for the A2 and A3 direction. लेकिन उससे भी पहले actually एक और thing is useful, yes, कि अभी हमने notice किया था by using the principle of angular momentum, where we had used moment equilibrium to see कि the stress tensor is symmetric, which means that I can manipulate this actually कि ये sigma 2 1 is going to be equal to sigma 1 2, और उसी तरह ये sigma 3 1 is actually going to be equal to sigma 1 3. And the only reason for me to do that is ताकि सब के सब ना ये sigma 1 phase के stresses में आ जाए. That's it. No other reason for that. So now you can see that this is sigma 1 1 with the partial derivative with respect to the x1 component. फिर वही phase का sigma 1 phase का 2 direction वाला stress differentiated with respect to x2 and so on. And I hope you guys can spot कि इसकी वजह से हमें थोड़ा सा फ़ायदा हो जाएगा when we try to write it down in either index notation या फिर direct notation, as we'll see just in 1 second. So let me also pop down the expressions for A2 and A3. इसमें exactly यही चीज़ होगी, but instead for the 2 phase, so that will turn into sigma 2 1 differentiated with respect to x1, sigma 2 2 differentiated with respect to x2, and so on. So we've got right the same thing, the equivalent thing, and for the third direction as well. Nice. Now maybe it's just easier to show you guys that these three expressions, ये तीन equations हैं, please note, this is equation number 1, this is equation number 2, and this is equation number 3. ये तीन equations हैं अलग अलग, they're not the same equation. These three equations can be combined together much more concisely in direct notation just by noting कि ये चीज़ क्या है. Well, I'll show you what it is and then we'll expand it to see how it makes sense. So, oh, okay, my animations have disappeared. Please just follow my cursor slowly ताकि, because of the lack of animations. So those three equations can be combined together in this direct notation, where here वो rho b और rho a तो straightforward है ना, इनका combine करना. It's just rho multiplied by the b vector, rho multiplied by the acceleration vector. So okay, perfectly nice and easy. Whereas the left hand side, sorry, the left hand term, this one is actually, uska first term is this one, then this is the second term and this is the third term. This is, if we expand it out and think about it, the scalar product between the del operator and sigma, the stress tensor. या फिर it is the dot product, या फिर in much better words, it is the divergence, इस dot को ना, the scalar product of any vector, या inner product of a vector and or tensor is known as a divergence when it's with the del operator. So this is the divergence of the stress tensor, or what it is in index notation, much more nicer to note down, that it is the differential of sigma ij with respect to xj. So note कि वो j becomes a dummy variable, right? So जब j dummy है, तो what we're going to be doing is कि when I is 1, somewhere here, this one, when I is equals to 1, then j is going to loop from 1 to 3 and we're going to add those terms. तो यही हो रहा है, sigma 1 फिर j 1 है, तो इधर भी नीचे 1 plus loop हो रहा है और add हो रहा है 1 2 with respect to x2 and then 1 3 with respect to x3. Same thing for when I is equals to 2 and when I is equals to 3. That is, this del dot sigma or the divergence of sigma can be more compactly written out, या फिर अगर if we don't know exactly कि वो del dot किस तरह होना है of a second order tensor with a vector, right? ये vector है del operator और stress tensor is a dyad. How does the dot operator work for these things? Then it's much better if we just note them down in our index notation, ताकि हमें पता चल जाएगा कि वो j dummy index है और किस तरह वो फिर manipulate हो रहा है basically. Okay, but just do note that this index notation is actually the divergence or the dot product between the del operator and the stress tensor. Perfect. So yes, so this equation written in tensor form, direct notation, जो हमने एक लिख दिया है, इसके अंदर it itself contains 3 equations for each direction, the x1, x2 and x3 direction, and that is why these are actually 3 equations of motion. इसीलिए ये equations लिखा हुआ है यहाँ पे, okay? क्योंकि scalar version के अंदर, इसके अंदर हर component की अपनी equation है, 1 2 3, which is just represented like so. Now, as I said, कि by the body does not need to be in under force equilibrium, so इसी वजह से उसकी एक acceleration arise कर रही है. But, and hence why it's called equation of motion, because there is an acceleration such that there is going to be some sort of a variable motion occurring. But sometimes what happens is, of course, we can get situations where the body is in complete equilibrium. It's under, it's a static problem. When it's under equilibrium, then we have that there is zero acceleration such that the same equations of motion can be written like so, with the zero tensor right here, zero vector right here, and this then becomes the equations of equilibrium. ठीक है जी. So just to point out again that the infinitesimal element will not be under force equilibrium, and that's why we have to apply the Newton's second law of motion to it. F is equals to ma, whereas the infinitesimal elements are under moment equilibrium, which is why we had applied the balance of angular momentum for वो जो second case हमने देखा था of the stress tensor being symmetric. Okay. Yes, what else is here? So there is an example, but just give me 1 second before that. One more thing that I want to point out. Okay, again, as for the case for the continuity equation, as and here that for the equations of motion, that these look new and unfamiliar to us, but this is actually just F is equals to ma. That's all that it is. या फिर अगर if you prefer the momentum version of it, this is just F is equals to dmv, that is the rate of change of linear momentum with respect to dt. But the difference is that when we used to write these things down, we were writing them down for individual particles or whole bodies, basically some finite thing like okay, oh ek puri gaadi hai ji jo ye kar rahi hai, and so on. Whereas when we write down this version of the equation of motion, this is for an infinitesimal element. Okay, hence why the appearance of the stress tensor and the body forces per unit mass and so on. Okay. Right, what time is it? 6:04, still got time. Okay. Yes, so let's just check one example. This is from Lai, example 4. So what we're trying to check is that in the absence of body forces, does the following stress distribution satisfy the equations of equilibrium? In these equations, V is a constant. ठीक है जी. अब ये this is looking like a little something funny, but जो T है ना, that's just it's just the stress tensor. Okay, so what was our equation of motion? That was the divergence of sigma plus rho b is equals to rho a, या फिर in its index notation ij comma j plus rho bi is equals to rho ai. So let's try it out. So clearly in the absence of body forces means there is no body vector, and now what we want to check is does it satisfy equilibrium or not. So let's just मतलब ये कि हम check करना चाह रहे हैं कि acceleration 0 आती है या नहीं. So let's just find what del dot sigma is. As you all can see from this index notation version, that is the divergence of sigma. मुझे उस तरह भी लिखने दें just to hone in के this scalar product is the divergence of sigma. इसको इस तरह भी लिखते हैं. This is going to be, इसको देख के मैं, by the way, मैंने याद नहीं किया हुआ. I'm looking at this while I'm writing this down. Clearly J is a dummy, so there's just I is the free index, so it's going to be a vector, and what it's going to have is when I is 1, sigma 1 1 with respect to x1 plus sigma 1 2 with respect to x2 plus del of sigma 1 3 with respect to del x3, और इसी के corresponding नीचे वाले which is will be del sigma 2 1 with respect to del x1, del sigma 2 2 with respect to del x2 plus del sigma 2 3 with respect to del x3, and last one as well. So let's write these down. Sigma 1 1 with respect to x1, ये रहा 1 1 with respect to x1 is clearly just this term is the one that's important, so that's going to be 2vx1. Then sigma 1 2 with respect to x2, ये रहा 1 2 with respect to x2, so that's minus 2vx1. and then 1 3 with respect to x3. Where is 1 3? 1 3 with respect to x3 is just 0. And in here I'm gonna have 2 1 with respect to x1. 2 1 अब सबको पता है कि 2 1 is equals to 1 2 because the stress tensor is symmetric, so it's this one. 2 1 with respect to x1, so that's minus 2v x2. x2 2 with respect to x2, ये वाला, that's plus 2v x2, and 2 3 वो भी 0 है, so plus 0. And then finally here I'm gonna have sigma 3 1 with respect to x1. 3 1 will be equal to 1 3, so that's just 0, plus sigma 3 2, और 3 2 जो है वो 2 3 होगा, वो भी 0 है, so that's also 0. And then finally sigma 3 3 with respect to x3, so that's this one. Sigma 3 3 with respect to x3, कोई x3 उसमें नहीं है, so that's also 0. So what are we getting? These all cancel out, so I just have a null vector, that is I just have 0 0 0, और ये तो 0 था, so this is equal to its acceleration. That's why yes, it does, the body, the infinitesimal element is under equilibrium, so stress distribution does satisfy equilibrium. ठीक, so see how useful the index notations are. मुझे तो I failed to memorize के okay किस क्या चीज़, so ये divergence of sigma निकालूँ तो उसकी क्या क्या term है, whereas if I just have it written out in index notation, that makes my life so much simpler. Okay, so as always I will try to provide you guys in both either direct notation or the index notation versions whenever I can. Okay, so I hope that makes sense. We've just looked at the application of the principle of angular momentum and the principle of linear momentum for an infinitesimal element to find out that actually the stress tensor is symmetric, and to rewrite Newton's second law of motion for infinitesimally small volumes. So next I'm going to just take a break here for the quiz. We've already gotten through 3 of our physical laws, and now we just got left the 2 final ones, which are the laws of thermodynamics. So we'll quickly jump into them and see how it goes, right? Okay, so I'm again, as with all of these, these are things which we are familiar with. But we're just formulating them for an infinitesimal element. So that's the same thing that we'll be doing with the first law of thermodynamics and the second law of thermodynamics as well. Now, just want you guys to have a little recall of what these laws were. So basically, the first law of thermodynamics is essentially the statement of the conservation of energy. ठीक, या फिर अगर आप वर्क और एनर्जी के टर्म्स में देखें, नॉट जस्ट एनर्जी, देन इट इज़ द स्टेटमेंट ऑफ how energy, or sorry, how work gets converted into energy essentially. So it is the relationship between the interconvertibility, okay, how work gets converted into energy, but essentially the overall it is just another way of stating the conservation of energy. Now then the second law of thermodynamics comes in, or that actually gives us a sense of the direction of what direction can that energy transfer be conducted in. Basically, not all energy conversions are reversible. So कुछ जो processes होती हैं, कुछ conversion of one type of energy into another. So for example, you guys can imagine कि mechanical work can, your mechanical energy can be converted into heat energy because of friction, लेकिन of course वो heat energy वापस हम mechanical energy में नहीं convert कर सकते, और उसका एक reason है, और उसका reason जो है, that is the second law of thermodynamics, which places, as I'm just stating right here, it places restrictions on the direction of some natural processes. ठीक है जी. So we'll see what these two are just shortly. Okay. Yep, as I just discussed, okay, by friction our mechanical energy gets converted into heat, but that heat cannot be recovered completely to be converted back into mechanical energy completely. Okay, perfect. So let's start with the first law and then move to the second law. I should put a little disclaimer here that you guys will be doing, I think, these two laws of thermodynamics in much more detail in your fluid mechanics courses, yeah, heat and mass transfer courses. So that would be, I think you have computational fluid dynamics 1 and computational fluid dynamics 2. Some of you may already be taking them if they're being offered this semester. So I hope that you would have gone through these in much more detail in those courses, but we'll just do them, we'll go through these very briefly here just to understand what they mean physically. But their sort of in-depth applications will be considered in the CFD courses basically. Okay, perfect. So let's jump into the first law of thermodynamics. And as we discussed, this is the conservation of energy, and hence why the equation that we're going to come up with right at the end is also known as the energy equation. Okay, so essentially the first law of thermodynamics just states, as I said, that the total energy of a system remains constant. But it's energy is one way of looking at sort of the same physical property. The other version of that is actually work, right? So for example, when we do work, we increase the energy of a particle or an object, or and so on. So that is, the first law actually deals with the interconvertibility between work and energy. Or what happens in effect is that basically, I think it's just best if I just read this one. Again, just stating that the total energy remains constant. And another way to say that is that when we're looking at the mechanical energy and the internal energy of an object, so when I look at the internal and the kinetic energy of an infinitesimal element, then however they are changing or however they are increasing must be equal to what work has been done on the element and how much heat has been provided to it. That is, the rate of increase in the internal and kinetic energy of an infinitesimal element must be equal to whatever work is being done on it and whatever heat has been provided to it. ठीक है? और यही स्टेटमेंट अमाउंट्स के बजाय अगर हम रेट्स के सेंस में करें तो फिर वी जस्ट गेट द सेम वर्जन ऑफ दिस, बट इंस्टेड ऑफ the principle of work and energy, we get the principle of the rate of change of energy and the power being provided to the infinitesimal element. Let's write that down mathematically. I think इतना बोलने के बजाय ज़्यादा आसान है if you just see it like so. So if I say that U is my internal energy and KE is my kinetic energy, then the rate at which my internal and kinetic energy are changing is actually equal to कि जो भी total power provide की जा रही है और जो भी rate of heat input है. ठीक? Makes sense, right? This makes sense, I think, to all of us. Right, so just to state each of these clearly. So U is, as I've said, the internal energy. और हाँ, sorry, just to point out, कुछ भी बोल नहीं है, everything is a scalar here. Of course, yes, total internal energy is a scalar. Good with me. Kinetic energy, that's also a scalar. Perfectly fine. And then this d by dt is the material derivative. So if I'm looking at an infinitesimal material element, So उस material element का क्या या particle का क्या change हो रहा है, that's why this the material derivative, and that is going to be the external power provided या फिर the external rate of work being done on that particle, and then finally the rate at which heat is being supplied to it, rate of heat input. बिल्कुल ठीक है. अब होना ये है कि what we're going to do is we're going to start to this is I think the one that we are very familiar with, but let's start to expand these out ताकि हम इसको एक ये तो पूरी body के लिए भी apply करता है ना या फिर entire systems and so on. So let's start to consider this for an infinitesimal element. That is, let's start to convert these into per unit masses and so on and so forth. Right. So first of all, yep, I want to introduce कि वो जो मैं infinitesimal particle को अगर देख रही हूँ, so that let's assume कि it has the volume of the particle and S is its outer boundary and it has a density rho. Okay, then थोड़ा सा ना मुझे I'm going to keep it here, the initial equation, and then start to introduce some things to manipulate this expression basically. Yep. So first of all, let's start with the internal energy. So let's change the total internal energy into the internal energy per unit mass. So फिर ये then this du by dt becomes just u dot, or this u dot of course is then just the small u dot integrated over the entire mass of the particle. Right? Nothing fancy if this u is the internal energy per unit mass. Then of course the integral over mass can be changed into the integral over volume if I introduce the density of the particle. बिल्कुल ठीक है. तो ये du by dt की term हमने sort of उसको infinitesimal version में convert कर दिया है. Excellent. Let's move on. Kinetic energy. So let's just keep it that way for now. There will be a reason you'll see के why this is a good idea. So इसको ऐसे ही रखते हैं अभी, इसको कोई infinitesimal version या integral versions में नहीं convert करते अभी. फिर आते हैं the power input to the particle. Now I want you guys to think about कि जो भी हम power input करते होते हैं किसी एक particle को या किसी body को even. So think about it. So for example, if I grab a ball and I do work on, I provide some power to it or throw it, and what do? एक तो कि I think it's pretty clear कि I've provided power to change its kinetic energy. That's one way of thinking about it. My external power is doing that. Next, let's say also कि कोई और example, ball कितनी अच्छी नहीं थी वो तो उसमें कोई deformation नहीं होती. अब clay की बारी आ गई चलें I guess. So I have that ball was actually a ball of clay, and if I do work on it, if I provide power, then I think you guys can all spot that I can deform it, right? That is, I can cause some internal energy to increase because of work going into deforming the object. So that is this external work done, जो ये P external है, that actually goes into two things. One is the power going into deforming it, and the other one is the change in or the rate of change of its kinetic energy. और बस यही दो चीज़ें हैं what the external power can basically be doing essentially. Okay, so अब आते हैं कि what is, and I know we haven't really talked about this, even though we've already now introduced stress, we've introduced strain and so on, but we haven't really talked about what is the energy being stored in a continuum because of deformation. So we'll leave that for now. Inshallah we'll come to it later on, but just for just jump to it basically is that this the power or the work being done, the rate of work being done into deforming a body has a neat little expression in terms of the stress within the body and the rate at which the deformation is happening. And that is basically this nice little conjugate of the energy being stored because of deformation is actually just this, the stress tensor multiplied by the rate of deformation tensor. Let me repeat this actually, sorry. This is a power, ठीक है? So this means कि इसके अंदर if I define the energy being the internal energy which is elastic, that is due to deformation आ रही हो, तो ये P deformation जो है ना, वो ये U deformation का internal energy stored because of deformation का rate of change है. It is d by dt, which is why I want to point out to you guys कि इसकी जो expression है that consists of the stresses, yes, but the stress conjugated or multiplied in a very particular way with this d. So if you, some of you may, I hope, recall that this d is something we've already looked at. This was the rate of deformation tensor. What this was is that it was the symmetric part of the velocity gradient. ठीक, याद है एक दफ़ा हमने इस डेल वी को ब्रेक डाउन किया था. डेल वी हियर इज़ बाय द वे द वेलोसिटी ग्रेडियंट. ये बड़ी पुरानी अब बातें हो गई हैं, लाइक अ फ्यू वीक्स बैक, लेकिन आई एम जस्ट ट्राइंग टू रिकॉल के दिस डी इज़ नॉट समथिंग न्यू. दिस वाज कि हमने वेलोसिटी ग्रेडियंट को जब सिमेट्रिक और एंटी सिमेट्रिक पार्ट में डीकम्पोज करते थे, तो देन वी वुड गेट द रेट ऑफ स्ट्रेनिंग, मतलब एक किस्म का रेट ऑफ डिफॉर्मेशन टेंसर, या फिर ऑल्सो द स्ट्रेन रेट टेंसर भी इसको कहते थे. ठीक, एंड द स्पिन टेंसर. ठीक, इसमें इसके अंदर रेट ऑफ रोटेशंस थी या रेट ऑफ स्पिनिंग थी, और इसके अंदर हमारी रेट ऑफ स्ट्रेनिंग थी बेसिकली. So when I am trying to find the rate at which elastic energy is being stored, then of course it makes sense that I am multiplying by the stress by some kind of a rate, and that rate is the rate of straining essentially. The only interesting thing, the next thing to point out is that this quantity right here, just the stress multiplied by the rate of deformation tensor, it actually gives us the rate of storing elastic energy per unit volume. Okay, why? Because the stress tensor is defined for a infinitesimal element, right? For an infinitesimal area. So that's why it makes sense कि when we do find it, वो हमें बिल्कुल ही एक infinitesimal per unit volume के लिए मिल रहा है. तो अगर हमें कोई उससे ज़्यादा बड़ी वॉल्यूम्स के लिए उसको डिफाइन करना है, then we do have to integrate it over the volume for which we want to find the rate of deformation. Okay, so that's just one thing to point out, that this D is not something unfamiliar. This is the rate of deformation tensor. Now, the next thing to point out is कि वो जो multiplication हो रही है ना, these are two tensors, two dyads, two second order tensors. तो इनको multiply करने के बहुत सारे फ़र्क तरीके हैं, और this particular one जिससे हमें stored elastic energy मिल रही हो, का rate मिल रहा हो, that is actually when it is actually ij and db ij. That is, both ij are dummies, which means that when I perform this tensor multiplication, I'm going to get a scalar. Okay, and that makes sense because wo jo power input hai, that is your power input for deformation, that is a scalar value. Power is a scalar value. Okay, so hence why it is this ij, और इसी को direct notation में मैं अगर लिखूँ, so right, this goes right back to I think the second lecture that we had, which was that this fancy little scalar product या inner product is a double inner product, या फिर it's a double dot product, और इसको direct notation में इस तरह लिखा जाता है. sigma colon D, colon D, okay. That is, it's a double dot product या डबल इनर प्रोडक्ट, दोनों नाम यूज़ किए जाते हैं उसके लिए. ओके, सो आई नो दैट दिस इज़ अनफेमिलियर कि ये कहाँ से स्ट्रेस को एक स्ट्रेन रेट से मल्टीप्लाई कर रहे हैं, बट जस्ट टेक माई वर्ड फॉर इट कि व्हेन वी फाइंड this double inner product, then we find basically what is the rate of storing of elastic energy in that per unit volume basically. So the total is then the integral over the volume. One more sneaky little side note in here, or I think you guys have noticed now already कि continuum mechanics, मैंने आपको कहा था, it is the basis of all mechanical engineering. It's crazy vast. तो बहुत सारी और चीज़ें जो अब हमारे पास टाइम नहीं था कंसिडर करने का इन द कोर्स, सो इसलिए कुछ इधर उधर साइड नोट्स के तौर पे आ रहा होता है. सो वन मोर साइड नोट इज़ कि दिस रेट ऑफ डिफॉर्मेशन टेंसर D, this is never did we ever say कि is this, what is this in terms of d by dt या फिर d by epsilon dt. That is never, even though हम कह रहे हैं ये rate of straining है इसके अंदर, लेकिन हमने कभी इसको in terms में, in terms of the green strain tensor या in terms of the infinitesimal strain tensor के rates के तौर पे कभी define नहीं किया था. उसकी ये वजह है कि unfortunately this D is not, it's not directly equal to this, neither is it directly equal to that. It's actually a little bit different from these two things. So that's why we haven't really discussed it. So इसलिए इधर ना sigma double dot product with D है, not sigma double dot product with E dot or so on. It's not this. But only for one nice little case, which for the 90% of engineering problems we consider because we look at metals, is the case when we have infinitesimal strains. Only for that case, that is for small strains, which we've talked about before, या फिर for small displacement gradients, as we discussed, only then is this D actually equal to the rate of infinitesimal strain tensor. Okay? So only for small strains does it become just this. Okay. Just some side notes for you guys. Anyway, moving back to our energy equation. So we were trying to convert this into an infinitesimal form. We've got our internal energy, excellent. Kinetic energy को भी हमने वैसे ही रखा है, we're just keeping it there. We also now have our external power provided converted into either the kinetic energy or the and the sum of the rate of elastic stored energy in it. So that's also something that we've got. We've got this, we've got this, we've got this. Now comes the time for the rate of heat being supplied to our infinitesimal particle. Right. Ab heat that's being input into the particle actually consists of two terms. One is any heat being generated within the volume, या फिर one is like a body term. So one is the rate of heat supply per unit mass, मतलब ये कि उसी के अंदर कोई अगर heat, कोई body heat generation हो रही हो. And then the second one is the heat being provided because of a heat flux going through its outer surface. Okay? So that is, let's define these two separate types. One is the body term and the other is the surface term. The body term को let's call it कि it's a scalar rate of heat being produced within per unit mass. And for the flux through the surface, let's define this Q vector, which is the heat flux describing के due to, let's say, conduction, what heat is being transferred through the surface of the particle. Then of course, then the total heat coming in By the way, ये याद रखिएगा ये rates हैं सारे. These are not some total, they're not some absolute amounts of heat. These are rates. So Qin is the rate, Qs is the rate of heat supply, and then Q is a flux vector जिसके अंदर भी एक rate होता है, per unit time होता है. Okay. So of course the total in is going to be the total heat being produced within it, which is going to be just the scalar Qs multiplied by the total mass of the particle, and then minus the heat flux going out, right? And yeah, I forgot to mention that flux vectors are defined positive going out of a surface basically. So if this is my particle, then the flux is going to be going out of it. So that's why there's a minus right here, and then this would be integrated over the entire surface. So this is a volume integral and this is a surface integral. Now let's, this is useful, ठीक है, we've already got it in terms of infinitesimal elements, but let me convert all of this into क्योंकि अभी देखें ना ये volume integral है, ये surface integral है. So let's try to convert them into just one type of integral, which is the volume integral. And to do that, I need to use something which, does anybody have any hints how can I convert a surface integral into a volume integral? Guys, none. So is there something, is there a theorem or something along those lines which somebody has already done for us like 100 years ago, which we could use? Dung, 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 dung. Okay. Anybody else who might recall?
Green's theorem तो नहीं मैं.
Okay, close enough. आप G तक पहुंच गए थे. That's the, it's Gauss's theorem basically, which is in other words also known as the divergence theorem. और अभी when I state it, I again we जब physically हम उसके बारे में सोचे ना, it makes a lot of sense, which is basically if I have the flux of a property going out of a surface, तो अगर ये Q is going out of a surface, then ये इसके बाहर जाने से इस वॉल्यूम के अंदर कोई चेंज हो रहा होगा ना इन Q, राइट? अगर Q बाहर जा रहा है तो इस वॉल्यूम में चेंज हो रहा है उसकी वजह से. So that's basically what Gauss's theorem or the divergence theorem do. That is, they state that this surface integral, the flux of anything going out of this surface, is actually equal to a volume के अंदर what change occurs in that same property. And this fancy little thing, which I hope कि अभी I just explained it physically, अगर if it's going out of the surface, if I find कि वो total कितना बाहर जा रहा है, that's the same as thinking of the volume and thinking of how much change is occurring in that volume. Does that, I hope that makes sense. So this thing is the divergence theorem या फिर Gauss's theorem, and I'm just going to apply it to this thing right here. I think you're actually right that it is also known as Green's theorem in 2D, but I will check that. Okay, generally speaking though, it is the divergence or Gauss theorem. Okay, so just applying that right here as I just written down, okay, whatever amount is leaving it through the surface must be equal to the whatever amount it's being changed by in the volume. So then this ये जो हमारी heat flux वाली term थी, that changes into this. Also I forgot to state that I have changed, what I've done is that the same old first law of thermodynamics that we'd written in, like so, I've changed it up with all of the things that we just discussed, which is कि U को हमने लिख दिया था in terms of the internal energy per unit mass. Kinetic energy we just kept as it is. Then P external we saw is the rate of change in the kinetic energy and the rate of storing of the elastic energy. या फिर it's the work done in the deformation, the power supplied for deformation. And then finally this is Q in, as we have just discussed. So what does that allow me to do? It allows me to simplify this, and I can spot basically that my kinetic energy terms cancel out. Isliye I've been sticking to keeping them around. So I don't need to convert them into an integral version. Whereas everything else is now an integral over volume. And now that's the neat thing, because if this has to be true for some large volume, तो इंटेग्रल वर्जन्स का मतलब यही होता है कि उसको इन्फिनिटेसिमल वॉल्यूम के लिए भी ट्रू होना पड़ता है. So that means कि this same term, all of this, if I collect all the terms together, then I can just remove the integral and consider it for an infinitesimal volume. That is, मतलब according to calculus अगर आप एक arithmetic कर रहे हैं तो इसलिए वो integral cancel हो सकता है, right? So that's why it just gives us our integral version या फिर our differential limit का version when the infinitesimal when we're looking at an infinitesimal element या infinitesimal volume. So this gives us our conservation of energy, your first law of thermodynamics, या फिर in other words the energy equation for our infinitesimal particle. Right? Just note what are these things. This is our rate of increase, your rate of change of internal energy multiplied by the density. Then I have my rate at which energy is being stored because of deformation. So actually इसको ना ज़रा physically सोचते हैं, ठीक है? ये तो हमारे पास internal energy का rate है ना, तो clearly internal energy के क्या aspects हो सकते हैं? One aspect is of course के अंदर उसके अंदर कोई stored elastic energy हो, और दूसरा उसका एस्पेक्ट क्या है कि उसकी हीट एनर्जी किस तरह चेंज हो रही है. एंड दैट्स इट. बस ये ऑब्वियस वही अगेन एनर्जी कंजर्वेशन स्टेट कर रहा है. So whatever is going to be the rate of change of the internal energy, that's actually going to be equal to the rate of change of the stored elastic energy plus the rate at which heat is being input into my my element basically. Okay. It's just the way to split up the internal energy consists of the stored potential energy and the heat energy. या फिर the heat energy is essentially the energy due to the vibrations of the particles. Okay. So I hope that makes some sense. As for all the other principles, just a new way of stating something old, stating something familiar. We've just been rederiving these expressions so that we can consider them for our infinitesimal material particles for a continuum. Okay. So any questions for the energy equation? Otherwise, I can move on to our second law of thermodynamics. Okay. So if no questions, let's quickly move to the second law of thermodynamics, and that's where basically actually let's start with the interesting part. The whole constraint on why we have a past and a future. Why is it that so many things are just processing or proceeding in one direction? Why am I getting old? Why are you getting old? Why aren't you getting young? And so on comes in from the second law of thermodynamics, which is basically related to the entropy of a system या फिर entropy of a particle even. So I'm sure you guys have considered it. वही बात है ना कि you must have considered entropy for systems or for large bodies or for entire bodies and so on. Whereas here what we're interested in is looking at that same second law of thermodynamics, but to look at it for an infinitesimal particle. This one is a bit straightforward when we're just considering it in the infinitesimal case. Lekin it's interesting to consider otherwise, right? So as we discussed, it's the second law of thermodynamics that dictates the direction of certain processes. So इसीलिए I just want to point out that whenever you guys, let's say, see something like this, a glass being put up again. Why am I saying put up again, right? When you're seeing this in this direction, I am sure that we all intuitively just can identify कि ये reverse direction में process show हो रही है. Okay, और उसका सारा ताल्लुक यही idea कि why are we so familiar with the concept of time moving in one direction is exactly because हम लोगों की ज़िंदगियाँ पूरी की पूरी are dictated by essentially this second law of thermodynamics, और उसी की वजह से हम सबको पता है कि this is an irreversible process, जिसकी मतलब ये कि इसकी एक ही डायरेक्शन हो सकती है. It cannot, it's just not possible, it does not fulfill the laws of nature if it's going in this direction. So this must be going in the this must be playing backwards, so to speak. Okay, and that is basically because of the second law of thermodynamics, which states essentially that the entropy of a system can only increase or stay the same. The entropy of a system cannot decrease. And this law of God essentially dictates that time will only be traveling in one direction, basically. Okay, so just इसकी हम derivation लंबी चौड़ी के अंदर नहीं जाएंगे कि what is the expression for entropy and so on. We're just going to pop in what the inequality is, or just to sometimes use it, although as I said, you should be considering these things in much more detail in your CFT courses, so that's why we will not be spending too much time on these. So just to remind you guys that entropy is a measure of the state of disorder in a system. So all systems are trying to basically the laws of physics essentially dictate that systems want to increase their disorderliness. They want to increase their entropy, or to the extent that then this law exists, this physical law, which essentially states that entropy कभी भी decrease नहीं कर सकती. अदनान, आपकी आवाज़ नहीं आ रही.
अब आवाज़ आ रही है?
हाँ जी, बोलिए.
Ma'am, I've basically never understood this concept of entropy basically. So मुझे मतलब इसमें काफ़ी confusion रही है always. Ma'am, how do we decide that if a system is in order or not? मतलब इस चीज़ की हमें डिसीजन क्या मतलब क्या पता कैसे पता चलता है कि सिस्टम ऑर्डर में जा रहा है या डिसऑर्डर में जा रहा है? तो ये चीज़ मुझे हमेशा काफ़ी कंफ्यूज करती रही है द बैचलर्स एज वेल. कैन यू डिफाइन ऑर्डर एंड डिसऑर्डर लिटिल बिट कि किस तरह उस चीज़ को
Sure, Adnan.
मतलब इस तरह से पहले सिस्टम आ रहा है तो चेंज हो रहा है, तो हाउ कैन वी से कि इज इट गोइंग टू एन ऑर्डर और डिसऑर्डर? ये चीज़
Okay, Adnan, I'll try my best, but I should warn you that I may not be giving you a satisfactory answer because I'm not an expert I don't really deal with entropy that often, right? So I would recommend that even though with whatever I'm about to say to you, if you're not satisfied, please do go ask or any one of the faculty members who specialize in fluid mechanics, because I think usme it's extremely important, right? Entropy comes in a lot. Whereas in solid mechanics, Not so much. बेचारे वो order वैसे ही रहता है almost. Right, okay, so just a little idea of orderliness and disorderliness. Okay, so let me see. Okay, let me just ask you. So consider कि मेरे पास सोच रही हूँ मैं. Give me a few seconds, please. Consider that I have a crystal structure. ठीक है, I'm sorry I'm borrowing my example from solid mechanics again. But consider that I have a crystal lattice और उसका ना मैं सिर्फ एक unit lattice बना लेती हूँ. Something like this. Okay. Now consider कि मेरे पास ये 1 2 3 4 5 6 7 8 atoms हैं और 8 locations हैं. ठीक है. सो इग्नोरिंग कि इनका ऑर्डर क्या होना है, मुझे उसके ना ऑर्डर में एग्जैक्ट इंटरेस्ट नहीं है, बट आई एम जस्ट इंटरेस्टेड कि ये 8 एटम्स इन 8 पोजीशंस में किस तरीके से अरेंज हो सकते हैं. सो क्लियरली वो एक ही मतलब वो सब फिल हो जाएंगे, तो एक ही तरीका है. So I just have one way of doing that basically. All of them will get fit into it basically. But now consider कि मेरे पास इनमें से 8 एटम्स के बजाय सिर्फ 7 एटम्स हैं, सच दैट ये एक खाली जगह है मेरे पास. और मेरे पास अब क्या हो गया, मेरे पास टोटल 8 स्पॉट्स हैं, लेकिन मेरे पास 7 एटम्स हैं. ठीक. So if I try to fill that situation up, then I have a larger variety, right? A larger number of options to go to. I could have this whole मतलब whole कह लें या खाली जगह जो है मेरी, वो या यहाँ हो सकती थी या यहाँ हो सकती है या यहाँ हो सकती है, यहाँ हो सकती है, यहाँ हो सकती है, and so on. That is, I have actually how many options? 8 options in that case. So this thing which is describing ke how many configurations can that system be in, that refers to the state of orderliness या disorderliness. जब मेरे पास सिर्फ एक था, एक ही तरीका है, then that's ordered. That's like I have no other, that's it, बस एक ही होगा, order है उसके अंदर. Whereas just because I removed and I had 7 atoms left and I still had 8 places to fill up, then I have created a larger number of possible configurations or possibilities. And those are then 8 फरक configurations. That is, वो system मेरे लिए इतना ordered नहीं है, क्योंकि मुझे नहीं exactly पता कि वो यही होगा या कौन सा होगा and so on. So this increase in the number of possible configurations of the system, that creates a higher amount of disorder. Right? So so that's just और ये देखें जिस तरह वो particle ये टूट रहा है. So in this state it just has one configuration, that's just the order. And then when I shatter it, then there are so many pieces that just by sheer just increasing the number of particles and how they can go together, how increasing the number of pieces, I've sort of created an increase in the disorderliness or increase in the number of configurations of that system. अब वो एक उधर पड़ा हो सकता है, एक इधर पड़ा हो सकता है, and so on. I realize this might not be so satisfactory, but that's basically how I think of it. It's how many configurations can you have that same system in, that measures the disorderliness of it. If you have loads of different options, then that's a very disordered system. Whereas if you don't have that many configurations, then that's ordered. But as I said, please Yeah. या फिर अभी भी I'm sure many of you have come up with ways to understand entropy. Would anybody else like to contribute? Would anyone else like to contribute? Okay, what is entropy?
आई थिंक मैम सभी लोग जो हैं वो उनको भी इतना ही शायद आइडिया है या ऐसे ही खामोश हैं।
कोई है ही नहीं पीछे अदान, सब चाय पीने गए हुए हैं ऑन करके। नहीं चलें, ओके, बट डू लुक इट अप। इट्स आई थिंक आई एम प्रीटी श्योर इट्स समथिंग दैट कीप्स, सॉरी
कह रहा हूँ सुन रहे कहीं नहीं गया चाय पीने।
it's something that bothers many of us, right? Okay, so unfortunately entropy also has something to do with the heat being supplied to a system. Just because when the state of energy, when you increase the internal energy of something, it starts to jump about. So it's so to speak, it starts to increase the entropy of that particular system. So इसीलिए this entropy inequality consists of essentially, or I may not have enough time to go into too much detail, which is just saying कि जो heat input हो रही है ना, so this again, sorry to just jump into it, just to point out, this is the heat being generated within the infinitesimal volume, and this is the heat being removed from it because of the flux going out of its surface. So together these two consist of whatever Q in is for the particle. So the entropy inequality states okay, the rate of change of the energy of that system must be greater than or equal to the change in entropy being caused by the supply of, or because of heat being inputted into the volume. Okay, it can never be less than it. मतलब ये कि जो हीट इनपुट करने की वजह से सिस्टम में एंट्रोपी इंक्रीज हो रही है ना, हमेशा या तो एंट्रोपी इंक्रीज उसके इक्वल होगी या फिर किसी और वजह से उसमें और ज़्यादा इंक्रीज हो रहा होगा. इट इज़ नेवर पॉसिबल, जस्ट एज एनर्जी कैन नेवर बी डिस्ट्रॉयड, इट्स नेवर पॉसिबल कि आप जितनी एंट्रोपी इंक्रीज करें बिकॉज ऑफ हीट, उसको कहीं और से आप रिमूव करना शुरू कर दें बेसिकली, इफ दैट मेक्स सेंस. वो हमेशा at least the change in entropy must be at least equal to the change in entropy being caused by the input heat. Okay, so just nothing else to it except that this is the entropy inequality, and I think I forgot to mention in this case this is again a rate version, so that's why this eta, this n looking symbol, I think this is an eta, this eta is eta dot, so that's the rate of change in the entropy per unit mass, and thus the total rate of change in the entropy of the entire particle involves the integral over the volume, and that must be greater than equal to the entropy being generated, the rate at which entropy is generated, or the rate at which entropy is leaving the control volume from its boundary, from its surface basically. Okay. Yes, इसको भी हम again इस del S के ऊपर, if we apply divergence theorem, then we can convert them all into volume integrals and then remove the volume integral such that we get this thing right here, which is the infinitesimal definition of the second law of thermodynamics. अब इधर प्लीज़ नोट वो n डॉट हैज़ नाउ बिन रिटन एज द मटीरियल डेरिवेटिव, इट्स dn by dt. सॉरी मैं इसको n कह रही हूँ, दिस इज़ ईटा, sure, it's the entropy per unit mass. And then this QS is the heat being produced, generated per unit mass. Rho is the density. Theta is the temperature, the absolute temperature. Absolute का मतलब ये कि Kelvin में होना ज़रूरी है उसको. And then that must उससे minus, फिर because of the divergence theorem applied to this term, वो divergence आ जाती है of that term. Sorry. So that's it. This is the entropy inequality, and this is dictating basically the direction of time for us. Okay, there is an example for it, but I'd like you guys to read through this example because, as I said, what is the time? 7:25. Still got 15 minutes. I'm emphasizing again that the last two, the first and the second law of thermodynamics, will not be heavily focused on in this course. So expect that they will be dealt in much more detail in CFT courses or CFT 1 and CFT 2, which I know you guys have. ठीक है, so इसकी वजह से I'm just keeping like a simple example right here, nothing too complicated, and I'll read through it with you guys as well because apart from just understanding what these things are physically, we're not gonna be solving too many numerical problems on the first and second law of thermodynamics. Okay.
मैम ये असाइनमेंट में भी नहीं आएगी?
आप चाहते हैं कि मैं डाल दूं?
मैम आप ऐसे ही वो लास्ट टाइम आपने कहा था कि ट्रांसफॉर्मेशन हम नहीं करेंगे स्ट्रेस की, तो ये इतना इम्पोर्टेंट भी नहीं है, तो वो आपने असाइनमेंट में दे दी
है। मैंने ये कहा था कि ट्रांसफॉर्मेशन इम्पोर्टेंट नहीं है।
तो आपने कहा था कि ये हम इसको वास्ट मेजॉरिटी में करेंगे नहीं, बस आपको एक टच देना है कि आप इस तरह कर सकते हैं, तो वो आपने फिर वो असाइनमेंट में भी दे दी।
हो ही नहीं सकता कि मैंने ये कहा। I think you might have अभी either I might have made a mistake, but other students can clarify. The most I might have said to you guys was
ma'am, I think you said this about Mohr circle.
I said this about Mohr circle कि Mohr circle को use नहीं करेंगे।
Yes ma'am, you said that this will not come in exams.
Okay. So मतलब ये कि the transformation of stresses using Mohr circle नहीं होगा, लेकिन the transformation of stress using the stress tensor approach or the tensor approach वो definitely होगा, right? क्योंकि अगर if I have made that mistake, let me clarify. The stress transformation is actually an extremely important thing जो हम इस course में कर रहे हैं, exactly because that is not the approach that you have been using for the past however many years. Whereas in this course, now that we have started to treat stresses like tensors, we are able to directly use stress transformation or directly use tensor transformation for stress transformation. तो if I have made that mistake, I apologize. मुझे तो ये याद पड़ा था कि मैंने इतनी डिटेल में बताया था कि मैट्रिक्स मल्टीप्लिकेशन के लिए खुद ही कैलकुलेटर यूज़ कर लें, आप लोग मैनुअली ना कीजिएगा और
मल्टीप्लिकेशन रिक्वायर नहीं होगी, हम टूल्स यूज़ कर लेंगे।
एग्जैक्टली तो मैं ये बातें क्यों करूँगी अगर वो कोर्स में होना ही नहीं है। So just again to clarify, please, stress transformation is extremely important and it will most certainly be part of this course. If I had ensued otherwise, please I apologize, ignore that mistake. मैंने इसीलिए इन डिटेल बताया था कि अपने कैलकुलेटर्स के अंदर 3x3 मेट्रिसेस की मल्टीप्लिकेशन से कंफर्टेबल हो जाएं आप लोग सारे। Okay? Has that been clarified sufficiently?
Yes ma'am, sorry ma'am, वो हो गया clear, sorry.
Okay, so coming back to this, इसको मैं ये यकीनन फिर भी कह रही हूँ कि फर्स्ट और सेकंड लॉ ऑफ थर्मोडायनामिक्स के हम न्यूमेरिकल प्रॉब्लम्स नहीं ट्रीट करेंगे इन दिस कोर्स, those will be 100% more significantly dealt in an expert manner in your CFD1 and CFD2 courses. So do remember that. ठीक है? So इसलिए just either I'm just gonna quickly run through just a simple problem of the application of our first law and second law of thermodynamics for a heat transfer problem. What's happening right here is that we have a body, let's say it's a 1D body, ठीक है जी, क्योंकि x1 की direction में ही वो defined है. So it's something like this, let's say, और x1 is equals to 0 है इधर, और of course x1 is equals to L है. And now what we know is that we have the temperature at this point being kept constant at theta 1, and at x1 is equals to L, it's being also theta 1. Okay, let's see, I may have made a mistake here, but let's carry on. I think this is a mistake, this should be theta 2. So ये मैंने क्या लिख दिया, stress के theta 2. So the temperature there is theta 2 and the temperature at 0 is theta 1 for this body. Whew. Okay, so now using the Fourier heat conduction law, or the nice thing about this Fourier heat conduction law, even though we haven't looked at it in continuum mechanics, is that it relates the heat flux vector to the grad of the temperature. Okay, so del theta correlate karta hai with the fluxes, heat fluxes basically. Where k is a constant, find the temperature distribution. Okay, find the temperature distribution. Okay, let's jump into it. So this does not have much to do with us finding the entropy or so on. So that's why I'm going to assume that it involves us using the first law of thermodynamics. Let me write down the first law first. The power input into deformation plus QS rho minus the divergence of Q is going to be equal to rho U dot. Okay. Interesting. Whew, right, let's think about this. So for this body, there is no information given about it being deformed. So I'm going to assume that there is no work being done in the deformation or energy being stored in the deformation. So that's why this is just 0. Next is there is also no heat source, no information about the heat source within the body given. So this is also going to be 0. Because there is no heat source. Now finally आ जाते हैं कि हमारे पास सिर्फ बचा ये कि the divergence of the flux must be equal to the rate of change of the internal energy. अब एक interesting बात पे आना पड़ेगा मुझे, which is to note कि the temperature of the body is kept constant. तो ये theta 1 पे ही रखा हुआ है, ये theta 2 पे ही रखा हुआ है. Now this requires some external knowledge to note कि अगर temperature of the body remains the same, then उसके अंदर और कोई deformation नहीं हो रही, then there is no change in its internal energy. That is because these temperatures are constant, they are remaining constant. So throughout वो body का जो भी temperature है वो वही रहता है. That is, it's independent of time. So this U dot is also 0. There is no rate of change of the internal energy. So all I'll have left with then is that the divergence of Q must be equal to 0. Perfect. So when I'm in 1D, 2D में तो कोई flux है ही नहीं, it's just a one-dimensional body, then that means that it's just the del by del x of Q1. Perfect. और Q क्या है? Q is equal to minus K into del theta by del x1 del theta by del x2 ये रहा ना del theta था and finally del theta by del x3. As we just said, it's just a 1D problem, so these things they don't exist. There is no second and third dimension. So I just have del by del x of minus k del theta by del x is going to be equal to 0. K is a constant, so uska differential just comes out. So I have k del squared theta by del x squared is equals to 0. Manipulating this further, k del 2 theta by del x squared. अब तो I think integration रह गई है is equals to 0. So what will I end up getting? Integrating this with respect to dx. So that is k del theta by del x पहले आया plus some constant a, and that would still be equal to 0. Then integrating all of this with respect to I may be beginning to make a mistake. I'm struggling a little bit with integrating the double differential, but I am trying. Let's see. Integrating this again. Then I get k theta plus ax as, and then another constant as x goes from 0 to L. Pretty sure I'm making some mistakes here.
When we apply the limits, I'm sure that we put x is equal to 0 and जब हम लिमिट्स लगा देते हैं तो ये b कांस्टेंट तो नहीं आना था मैंने बताया
पता नहीं अदनान, I'm thinking about it. By the end of the class energy levels इतने low हो चुके होते हैं हम सबके ही, I think दिमाग भी नहीं चल रहा होता. मुझे ऐसा भी लग रहा है कि मैंने separation of variables भी ठीक नहीं की थी, या वो भी एक और मसला है इस वक्त. Sorry guys, I am struggling to think about it, so I'm gonna pop up the solution that we see what happens. But I hope कि हम सब will go back to taking a look at it. How do we integrate this? Just thinking about that. Yep, इधर तक तो we had gotten. Oh lovely, I just given the solution rather than finding the integration. Sorry for this. I'll spend some time figure this out, the integration from here to here. And then get back to you guys, okay? So, please.
Excuse me, ये next lecture में ये example दोबारा repeat हो सकती है?
Next किसमें? Sorry, next lecture में?
Yes, ma'am.
तो फिर अभी हम बिल्कुल ही छोड़ दें.
I think next lecture में कर लेंगे.
Okay. चलें. Sure. I am also, my brain is beginning to turn off. So I'm going to agree with you guys. So we'll pick up from here next time. Just as I said, don't worry too much about the numericals of the first and second laws, because वो आप सारी जो लोग फ्लूइड्स में जा रहे हैं वो हर वक्त यही चीज़ें अप्लाई करते रहेंगे. So and Navier-Stokes and whatnot. So we'll just conceptually deal with this. So everything that we've discussed, के first law of thermodynamics की वो individual terms क्या होती हैं, do understand those in depth. And then for the second law, why is it that dictates the direction of some processes, right? But that's about it. Anything more than that is beyond the realm of this continuum mechanics. Okay, so we'll restart next time with by completing this example. And then we'll also move on to, now that we've got our universal physical laws, then we'll start to look at some laws which are only applicable for particular continuum media. Okay, so we'll start to specify in much more detail, okay, when we look at solids, what further laws hold true, and then also later on when we look at fluids, what particular laws hold true for those. Okay, so that's the next step in our journey in continuum mechanics. Okay, all right, thank you all for your patience. That's it for today. I'm still around for 5 to 10 minutes for anybody who would like to discuss anything or any queries related to this, to the lecture.